We usually think of brilliant code as some huge, complex piece of software. But what if I told you that some of the absolute cleverest, most important code is totally invisible? It's running billions of times a day right inside your processor. Today, we're going to pull back the curtain on a tiny masterpiece of hidden genius. So just imagine for a second, what if the most elegant, the most efficient bit of programming on your entire machine wasn't in your favorite game or your operating system, but it was this one single kind of cryptic-looking line of code. This is XOR EAX EAX. And believe it or not, it's an incredible piece of engineering that's hiding right under our noses.
Now, to really get why this little instruction is so special, you first have to understand why it's so weird that we see it so often in the first place.
So check this out. If you actually look at which instructions your computer's CPU is running most of the time, you see the stuff you'd expect, right? Things like move to move data around or add for math. But then there's this one that just sticks out like a sore thumb, that tall bar right there. It's XOR, which stands for exclusive OR. And that's just odd, because back in the day, XOR was a specialist. If you were digging through some old code and you saw a bunch of XORs, it was a dead giveaway you'd found something very specific, like an encryption routine or maybe some fancy graphics trick. It was not your everyday run-of-the-mill instruction.
Which leads us to the big mystery here. Why on earth are our modern computers running this specialist instruction millions, even billions of times a second? What is it actually doing?
All right, to crack this, let's first look at what this instruction is trying to do, and then think about how a normal person would try to do the same thing. It turns out this is all about one simple task: setting a CPU register, which is just a tiny little spot of super fast memory, to 0. The logical human way to do it is on the left: MOV EAX 0. It basically just says move the number 0 into the spot. Couldn't be clearer. But on the right, that's what our compilers, the tools that build our software, choose to do. They use XOR EAX EAX. So, why? Okay, the first piece of the puzzle, our first clue, comes down to something really basic: size. How much space the instruction literally takes up. And this table just lays it all out perfectly. This is the actual machine code, the ones and zeros, well, hexadecimal, that the CPU reads. The obvious move instruction, you can see it there, takes up 5 whole bytes of memory. Now look at the XOR instruction. It's just 2 bytes. That is a 3-byte saving. Now, I know what you're thinking. 3 bytes, who cares? In a world of terabytes, that sounds like nothing. But you have to remember, this isn't happening once. This is happening constantly. Those 3 bytes saved over and over and over add up incredibly fast. And why does saving these bytes matter so much? Well, for one, it makes the final program smaller, which is always good. It uses less memory. But the big one, the really important one, is the CPU's instruction cache. That's a tiny, super fast bit of memory right on the chip that holds the next few instructions. The more instructions you can cram into that cache, the faster your CPU can run without waiting. It's a huge deal for performance. But hey, saving a few bytes? That's just the start. The real magic, the true genius of this whole thing, is what the CPU itself does when it sees this instruction. So let's get to our second clue: raw speed. This little trick is so common and so important that it actually has a name. It's called a zeroing idiom. And you can think of it like a secret handshake between the compiler and the CPU. The hardware, the chip itself, is built to recognize this exact pattern and treat it as a special case. So here's what goes down inside the silicon. First, the CPU spots the pattern. Then, its brainy out-of-order execution logic immediately realizes something crucial. The result is always going to be 0, no matter what was in the register before. This is massive because it breaks what's called a dependency chain, which can really slow things down. And then, it does something that's just mind-blowing. It does something that almost sounds like it breaks physics. It completely removes the operation from the line of things to do. That's right. The instruction effectively takes 0 execution cycles. It is so perfectly optimized that the hardware makes it cost literally nothing to run. It's free performance. And just when you think this trick can't possibly get any smarter, there is one last beautiful layer of cleverness, especially for our modern 64-bit computers. You might be thinking, okay, wait, on my 64-bit system, I've got 64-bit registers. The big one is racks. So why are we still using EAX, which is just the 32-bit version? Wouldn't it make more sense to use XOR RAX RAX? Well, the answer is another incredible hardware optimization. The folks who designed the x86-64 architecture put in a special rule. Anytime you write to a 32-bit register, the hardware automatically fills the top half of the full 64-bit register with zeros, for free. So by using the smaller, faster zero-cycle XOR EX, EX, you get the entire 64-bit register zeroed out. It is quite literally the perfect way to do it. So let's just step back and put all these clues together. Let's appreciate the quiet, hidden genius of this one little instruction. What we have here is an instruction that gives us two massive wins for the price of, well, nothing. It saves valuable space in our code, which makes our programs smaller and lets them live in that fast CPU cache. And two, because of that special hardware idiom, it saves execution time. It literally costs 0 cycles to run. And what this really is a beautiful dance between software and hardware. The people writing the compilers knew they could use this trick, and the engineers designing the CPUs knew the compilers would use it, so they built the chips to make it as fast as physically possible. It's an amazing collaboration. It's really a tribute to decades of this kind of invisible, clever optimization that makes our computers feel as fast as they do. So yeah, next time your computer feels really snappy, you can just give a little nod and say, "Thanks, compilers." And that kind of leaves you wondering, right? If this much thought, this much sheer genius can be packed into a single 2-byte instruction that nobody ever sees, what other incredible optimizations are firing away billions of times a second, hiding deep inside your computer right now?